Today we're talking relays. Let me wrestle this wiring loom on here and find a relay. So this is a relay and it's essentially just a switch. This is a switch. This switch is activated by your finger. A relay is a switch which is activated by a small current. So it uses a small current to control a bigger current. And if you think back to when we talked about the starter motor and we looked at the solenoid there, the solenoid is really just a king size relay. It does exactly the same job. A small current from the ignition key is used to turn on a massive current from the battery over to the starter motor. So switching big currents directly requires big switches, and they're heavy and they're relatively expensive. But these days, most things maybe, are controlled electronically by microchips and engine computers. The cooling fan is an example. Here's a cooling fan from this engine. Now the cooling fan is controlled by the ECU. The cooling fan is electrical and the ECU is electronic. The ECU, here's the ECU, monitors the coolant temperature. So it looks at the coolant temperature sensor, reads the value of the temperature of the coolant and turns the cooling fan on and off as it's needed. Now the ECU can output about 1 amp of current, but as we saw earlier, this fan takes about 7 amps. So between the fan and the ECU sits a relay that uses that small current from the ECU to turn the fan on. Now it helps to understand that a key difference between the electrical items and the electronic items, or between electrics and electronics, is the amount of current involved. When we talk electronics, we're normally talking about low currents and low voltages, little wires, thin wires, and traces around a circuit board like what's inside here. Now, electrical or electrics, that means usually bigger currents and thicker wires. And relays are often the interface between electronics and electricals. So, as we've seen, a relay sits between this electronic ECU and the electrical fan. Now, today, using relays is essential for electronic reasons, but even before electronics were scattered all over the car, relays were used because they allowed engineers to use thinner wires and smaller switches, and those are both lighter and cheaper. And aside from electronically controlled relays, there'll often be a relay where a mechanical switch is too small to handle the load. So maybe you've got a very delicate little switch on the dashboard handling a massive load somewhere in the car, a powerful accessory. Rear window defroster. Little switch, big current, relay. Interior light, little switch, little current, no relay. Headlights, little switch, big current, relay. Let's have a look inside this thing and see how a relay actually works. So automotive relays like this one, they're all based on an ISO standard in terms of the size and the layout of the terminals underneath. So this relay that we look at will be exactly the same as all relays that you're going to come across. On the outside of the casing here, you can see we've got some specifications. They're useful. We talk about those shortly. I've hacked off the plastic housing so we can have a look at the internals and actually see what's going on here. Now, first off, what we can see is that we've got things inside here that actually physically move. This is an electromechanical relay. That means it uses electricity and mechanical movement. And wherever there's mechanical moving parts, there's scope for failure. So there's an electromagnet here, which is turned on and off, in our case by the ECU, which is controlling the fan. And the ECU, or the input current here, comes into this coiled wire here, energizes this electromagnet and pulls on an armature here just at the end. And that pulls the armature into contact with a terminal. So what we have is, if we look at the underneath, we have 2 small terminals which control the current running through the coil, and then we have 2 larger terminals which provide the power that is being switched on and off. So those are the contacts, basically. Those carry the high current, so that's the high current side. So as the coil is energized, it pulls this armature towards, makes contact, closes that circuit with the high current running in it, and the high current runs out through the relay. So I've brought the relay over, I've connected up some power underneath, and as we make contact here and put a current across the coil, you can hear that clicking noise. And that clicking of the armature moving sounds a little bit like a turn signal or an indicator, right? When the flasher is working on the indicators in a car, you can actually hear the relay clicking on and off. And that's a sound that's so useful that even the most fancy cars now play the sound of a relay clicking through the speakers so that you know the indicators are on. A flasher unit that's used for those turn signals is a specialist type of relay that includes a timer. So you can see as we contact this, the coil is energized and it pulls that armature and makes contact. So in its natural state, this relay is off. And it's only when we apply current across the coil that it switches on. It's known as a normally open or an NO design because the outputs are normally open. You can see on the actual casing here, we've got NO written, which means normally open. There's also normally closed or NC relays where the contacts are closed unless we apply current, in which case they become open. So NO or normally open relays are by far the most common and the most useful. There's an interesting detail on this relay. If you take a close look inside, you'll see that we've got a resistor connected across the coil in there. Now, what happens is when the ECU turns on the coil, it creates a magnetic field. When the ECU turns off that current, the magnetic field around the coil collapses instantaneously, and that collapse is a huge change in the field, and it actually induces a voltage into the coil itself. That voltage can be hundreds of volts, even though there's almost no current, but the voltage alone can be enough to damage the ECU or any electronics that are connected to the coil. It kind of travels in reverse, known as a voltage spike. So any relay which is connected or controlled electronically will include some way of suppressing a voltage spike. In our case, that's why we've got this resistor in there. You might find them made from diodes as well. And whatever this voltage suppression is going to stop this voltage spike from happening. Now, for relays which are controlled by a switch, there's no need to suppress the spike because the switches don't care about that fraction of a millisecond or a nanosecond or a microsecond or some small part of a second. So when you're dealing with electrical issues, you want to turn to the wiring diagram. And Mazda's diagram for the Miata even helpfully includes, in the first couple of pages, an introduction to relays. It says, the current flowing through the coil produces an electromagnetic force, causing the contact to open or close. Brilliant. It's intriguing to me that they would include that because you've got to be pretty experienced to understand these wiring diagrams. Anyway, if we look at our cooling fan, we can see right here a cooling fan relay. So we know we have a relay in the circuit with our cooling fan. Now, as we said, for automotive purposes, all relays are based on an ISO standard. There's two common types on cars. We've got this one, which is a micro relay. It's rectangular in size. And there's also a mini relay, which is square and slightly bigger. So micro is smaller than mini, which I guess is like USBs, maybe. And there'll often be a rating on the case for the amount of current that the relay can take. In our case, we don't have one here, but we do have the voltage and that it's normally open. Normally a relay like this, you're looking at 25 to 40 amps. So most relays that you'll come across are of a plug-in type like this one where it clips into a connector. You might come across a surface mount relay. It's unlikely on a vehicle, but possible. These ones are preferred because you can take them off and test them and replace them when they're faulty. Now, depending on where they live, you may also find a relay with a rubber hood or some sort of weatherproofing. There's also specialist relays like flasher units, injector relays, glow plugs, which have specialist functions. Okay, let's say you want to check a relay. The first thing you've got to do is to actually find that relay, and that's probably the hardest part. So the relay could be in the fuse box, and there might be more than one fuse box. There's one here, there's one inside the vehicle here. They could also be in a box of relays, which might be in the engine compartment near the fuse box, might be under the dashboard, in the footwell, somewhere like that. In our case, for the cooling fan, we've got three relays here underneath this plastic cover, so we need to lift that off. Now, to check a relay, in theory, you could check it on the car, but you're much safer, particularly on a relay that's controlled by the ECU, to take the relay out and test it off the vehicle. Then you need to identify your wiring connections. Now, you can look up a wiring diagram for these ISO relays. They're all of the same type. A mini relay, no, this is a micro relay. A micro relay like this one, in either case actually I think, they have different sized terminals. So the smaller terminals or the thinner wires coming off this are always going to be the supply to the coil, where the bigger terminals, 6.3 millimeters I think on this one, are the main current, the switched current, the high current side of the coil. The other thing that you can do is you can look at numbers. So sometimes you'll find numbers imprinted on these terminals, and they come from a German standard. I think it's a DIN 72757, something like this, which has a series of numbers standard across an entire vehicle, which tell you what that particular terminal, that particular electrical connection does. So I think we've got 85 and 86 at the coil side, 30 is the common, and 87 is the switched high current terminal. But you can look them up in that standard, if I've remembered the number of the standard. Interesting standard there. And also international, German standard, but used internationally. So having identified which are your terminals, so we've got 2 for the coil and 2 for the high current side, we can then do some tests and actually work out, is this thing working? So we bring the multimeter into play. Let's switch this across to be in resistance mode, and we turn on the sound because we have beeps. Lovely. Okay, so we test first our coil side. And we've got our 2 terminals here for the coil, and we expect to see some resistance across there, but not too high, not too low. We're looking for about 80 ohms, something like that, some reasonable number. What have we got here? 97 ohms on there, so that's good. That's kind of what we expect to see. If that was open circuit, then we know the coil has a break in it and it's no longer working. So, having tested that, we can now test our high current side. We know this is NO, normally open relay. So we expect to have an open circuit here. We don't expect to see a resistance across here. Let's see what we've got. So it stays, you know, OL. As I bumble around here, you could probably do this in a more elegant way. But we expect across this output side to find an open circuit, which we do. The next thing you would want to do is you would, as we've done here, in fact, let's just use this one that we're already connected to, you'd want to apply 12 volts across the coil and listen to see, does the relay click? And then you leave your 12 volts across the coil, you would measure for continuity across the 2 main contacts, and hopefully we hear a beep. There we have it. So we know that this relay works perfectly, even though I've butchered it. There we go. Always a useful tool for diagnosing these things is to make yourself up a lead which has just, you know, a spade connection on the end of various different spade sizes, so you can plug into terminals and you're not, as I was doing there, attempting to balance these things around. Much more logical, if I was feeling intelligent, to attach this to here and then apply that to the spade. Failures. Dun, dun, dun. Relays, they're pretty sturdy, but they do fail occasionally. Every time the relay operates, there's a small arc of electrical current that chips away at the contacts inside here. When the armature closes, there's an arcing between the 2. And you've also seen how delicate the coil wire is inside here. There's a diagram somewhere of a lifespan for a relay that shows that the lifespan, or the estimated number of switches that it will make, contacts, is related to the amount of current going through that relay. So it's interesting that a relay carrying a higher current will fail earlier than a relay carrying a low current. But you know how to test them, and you know everything about relays. I think we're done here. Moving on.